All right, welcome to the second midterm edition of Physics 8A. Now I realize that there's very few of you currently online. I think it's a total of 9. Yeah. But I'll assure you that being online now is a good thing. As you probably have noticed, angular momentum and its conservation is not the most, well, it's confusing. In part because it deals with rotating motion. So as usual, if the 9 of you have any questions about what I'm doing on the board, or after I've written something on the board, please do ask. Today, we'll finish off angular momentum and likely start and perhaps finish statics. And we could do statics that fast because we're actually only doing a small sliver of the chapter. And I'll talk about that, well, when we start. Last time we met, last Thursday, we introduced the concept of angular momentum. We talked about when angular momentum is conserved. We talked about the angular momentum of a point particle, and we did an example. Today, I want to do 2 more examples for you, each one successively more complicated or more complex in order to, well, introduce new concepts to you as well as tell you how to solve problems. So the second example I want to do for you is the one on the board. This is, once again, a frictionless table, so you're looking down on the table. That means gravity goes inward, and I don't have to worry about gravity because everything's frictionless. Right? This is a rod with length L and mass big M, and it's sitting on this table, and I'm telling you, it's just sitting on the table. It's not being pinned to the table by a nail, for example, like the rod on Thursday was. It's just sitting there. I have 2 masses now, both of mass little m, and they're moving this way. One has velocity v naught to the right, the other one has velocity 2v naught to the left. And you're told that they collide with this rod simultaneously. In other words, they collide when a rod is here and at rest. And after they collide, well, the 2 masses stick on the rod. I want to know the velocity of the center of mass of the rod, how fast it's moving, and knowing that it's most likely rotating, I want to know the angular velocity of the rod as it rotates about its center of mass. Now, if you're presenting a problem like this on a homework or an exam, first thing you should realize is that because this is a frictionless table and because the rod is not anchored to it by a pin, that rod can move. That's why it's moving after the collision, or it can move after the collision. The second thing to note is that I don't know the direction that the rod will be moving, but I do know that the initial velocities were all in the horizontal direction, which means that the center of mass of the rod will likely move in the horizontal direction as well. I don't know if it moves to the right or to the left. That's okay. I'll just represent the velocity by a capital V. If V is positive, I guessed right. If V is negative, it's just moving in the opposite direction, and we won't count off for it. The third thing is that omega, because this is a freely moving body, omega is rotating about the center of mass of the rod plus the masses. Okay? So I have to think about where the center of mass for that system is. And we'll get to that. But the first thing you should do when you get a problem like this is go through the litany of conservation laws. First, you should ask yourself, is energy conserved? And the answer is, who knows? Probably not, but I don't know. Not a priori, not right now. The reason why you don't know if energy is conserved or not is because, once again, you don't know what is the force, what is the nature of the force that the small rod exerts on, the small mass exerts on the rod. You don't know if that force is conservative or if it's non-conservative. You just don't know when this point mass hits the rod. And because you don't know, you can't conclude that the energy is conserved or not, which means you can't use energy conservation. Everybody okay with this logic? The second conservation law you should look at is momentum. And since all the action occurs along the horizontal direction, you can ask, is momentum is conserved? And at this point, you should remember that momentum is conserved if there are no external forces acting on this system in the horizontal direction, the system being the 2 point masses and the rod. And there isn't. All the forces are internal to the system because, unlike the example on Thursday, this rod is not pinned to the table with a pin. So the table doesn't exert any force on the system, which consists of this mass, and this rod. So we know that momentum is conserved. And the last question is angular momentum conserved? And once again, well, for one thing, angular momentum, it turns out, if you want to see if it's conserved or not, depends on where you choose your origin in general. Okay. Since this body moves, I'm going to choose my origin to be at the center of the rod, center of mass of the rod. Right there. Now, all the torques exerted on the system is internal to the system. There are no external torques. Whatever torque the mass exerts on the rod exerts back on the mass. The same thing for this mass. Since there are no external torques on the system, I know momentum is also conserved. Okay. This is hands down the hardest part, tell you the truth, of one of these type of problems, determining what's conserved and what's not. And I now know that momentum and angular momentum is conserved, so I do my usual thing. I first write down the initial momentum for the system. Since this guy moves, it's mv naught. Let's do it right, it's positive. This guy doesn't move, so it contributes no momentum to the system. This guy moves to the left, and its momentum is m times 2v naught. There's a negative sign because it moves to the left. So that is the total momentum of the system initially. I also need the initial angular momentum because I know angular momentum is also conserved. In this case, since my origin is here, these are point particles, and I'll use the fact that the angular momentum of a point particle is p times the distance of closest approach. This is the magnitude of the angular momentum, so it's positive. This guy has a momentum. The distance of closest approach to the origin is L over 2. It tends to rotate clockwise about this point, so it's negative. This guy has a momentum. It's m times 2 v naught. The distance of closest approach to my origin is once again this much, which is L over 2. It tends to rotate this way, which is also clockwise, so it's also negative.
Sorry, can you repeat what B is again?
B is the distance of closest approach. It's the closest this particle will get to your origin. Okay?
Oh, right. Okay. Thank you.
You're welcome. Okay. In the final system, well, we have to look at the final momentum. Now remember, momentum, what I really mean by momentum is the total momentum of the system. Now, this guy and this guy, as well as the rod, are always all rotating, but I can treat the two masses in the rod as one big mass, centered at its center of mass. And I treat it as a particle, so that particle has momentum. The total mass of that particle is this mass, plus this mass, plus the mass of the rod, times the speed of the rod, v. This guy is rotating about the center of mass of this rod. And since my origin is here, that means that the final angular momentum is the rotational inertia of this system, the rod with two masses at the end, times omega. Now, I have to find omega, and remember that this rod will be rotating about its center of mass because it's free to rotate, right? That means I need to know the center of mass of the system. Well, I know the center of mass of the rod is at the center of the rod. This mass is on this side of the rod. This mass is on this side of the rod. So the presence of these two masses doesn't change the center of mass of the system away from that of the rod. In other words, the center of mass of these two masses plus the rod is once again at the center of the rod. This mass balances out this mass, so to speak. And that means that the rotation inertia of this rod is, of the system, the rotation inertia of a rod about its center plus the rotation inertia of this mass rotating with a radius L over 2. So it's m times L over 2 squared, plus the rotation inertia of this mass moving in a circle at a distance L over 2 from the center of mass. Okay. Or, since L squared is common in each, I'll factor it out. I have a 1/12 big M, and I have two of these M's divided by 4, or 1/2 little m times L squared. That's my rotation inertia.
Wait, so when you said that the mass is balanced out, why did, or how did that change your calculation of inertia?
It just, well, it tells us that we should calculate the rotation inertia about this point. It tells us where the center of mass is. And remember that this should be I of the center of mass for the system, because that's what it's rotating about. Right? So it tells us that we should calculate the rotation inertia about this point, which is the center of mass.
Okay, so if like both masses are on the same side of the rod,
That's right.
do that.
That's right. Then the center of mass would be moving upwards a little bit towards the two masses. And you would change your calculation. It'll be a real big mess.
Okay.
Okay.
Professor, why is it 1/2 and not 1/4? The square.
Here? Oh, because there's two of these. So there's a m over 4 and another m over 4.
Okay, thank you.
You're welcome. Momentum is conserved. That means that P naught, which is mv naught minus 2mv naught, or negative mv naught, equals m plus little m is 2 little m. And that means that the speed, the center of mass velocity, is negative little m over 2 little m plus big M v naught. In other words, it's actually moving to my left. That's okay. I just guessed wrong. Angular momentum conservation says that the initial angular momentum is the final angular momentum, which means that, well, since these are both negative, I would add these two with an overall negative sign. That's L over 2 plus L, which is 3/2 L. That's equal to I omega, and I is this mess. Or omega is negative 3m over 1/6 big M plus little m v naught over L. And it's negative because after the collision, it's going to be rotating clockwise this way as it goes down. Okay. So, as you look at this example, you notice that, hey, once you got these, right? Once you got the initial and final momenta, initial and final angular momenta, everything's straightforward. It becomes just an algebra problem. I didn't want to say just an algebra problem. It becomes an algebra problem. The hard part is everything that comes before. Knowing what's conserved, what the angular momentum is, being able to calculate the angular momentum, being able to, or actually write down an expression for the angular momentum, write down an expression for the linear momentum, and so on. That's the hard part. Questions? Cool.
The situation is, so it's basically it's rotating and also, like the entire rotating rod is also moving.
Translating.
Okay.
It's rotating and translating. The center of mass is moving, and it's rotating about the center of mass.
Okay, thank you.
Yeah. I was trying to, there's always pictures of these inside movies where an airplane or a spaceship gets hit and it goes flying outwards, rotating and moving in a straight line. That's what it's doing, basically. Okay, this is the second example, the last example on angular momentum. After this, we'll transition over to statics. This is once again a frictionless table. And I'll tell you that on this table, you have a rod. It's not anchored to anything. It's spinning with some initial angular velocity omega. All it's doing is sitting here and spinning around its center of mass. Okay? Then you put a little mass right here so that this little mass will collide with the rod will rotate around and smack it when it's at 90 degrees. Afterwards, well, you're told that the collision between this mass and this mass in the rod is elastic. In other words, you're told that energy is conserved in this collision. You're just told this. After this little bit mass gets smacked by the rod, it starts moving. It'll be moving in this direction because this gets hit at 90 degrees right here. The rod will start moving, and it may or may not be rotating. In other words, after the collision, this mass moves to the left, the center of the rod moves to the right, and it might still be rotating. We just don't know. Okay. I would like to know this U, this omega, and this V. In other words, I want three quantities. Now, like every conservation law problem, I would strongly suggest you draw this, the initial state, and you draw this, the final state. And then you go through your litany of conservation laws. Well, I already know energy is conserved because I was told that the collision was elastic. So I already know energy is conserved. Next, I know linear momentum is conserved because the rod is not anchored to the table, and there's no external forces on my system, and the system consists of the rod and the point mass. I also know that angular momentum is conserved because, well, all the torques acting on the system are, well, there are no external torques acting on the system. And actually, it doesn't depend on where you're choosing your origin. There's just no external torques, because that's because all the forces are internal.
Could you provide an example of an external torque?
Well, no, because I'm doing angular momentum conservation. And if there's if there's an external torque, then angular momentum wouldn't be conserved.
Or like what would an external torque look like?
It's a force acting on it from the external to the system.
Okay.
Yeah. Okay. Which means that all three conservation laws apply to this system, which is why I want to do this example. That means I should write down the initial momentum, initial angular momentum, initial energy. The initial momentum is 0 because the center of mass doesn't move. The center of mass of this rod doesn't move. The center of mass, this mass doesn't move initially. There is, however, angular momentum because this rod is rotating about its center of mass with angular velocity omega. And this omega is positive, right? Because it's rotating counterclockwise. Since it's rotating about center of mass, its rotational inertia is 1/12 mL squared omega naught. Or if you don't mind, I'll just write it as I omega naught, because I'm going to write down I a lot in this problem. I is 1/12 ml squared for this problem. And the only contribution to the energy is due to kinetic energy. There isn't potential energy anywhere. So that the initial energy of the system is just a rotational kinetic energy. It's 1/2 mi omega naught squared, because that's how fast it's rotating at the beginning. The final system. The final momentum of the system consists of this little mass, negative mu, plus this rod, which is moving with, its center mass is moving with velocity big V. And that's it. The final angular momentum is, now remember, I chose my origin to be at the center of the rod initially. Why is that important? Because I have to calculate the angular momentum of the system. This guy is rotating about its center of mass. So it has an angular momentum. It's I omega. It's positive because I'm drawing this as though it was positive. We'll let omega determine its sign at the very end. This mass, however, is moving to the left. And so it has an angular momentum because it's a point particle. The distance of closest approach is just this again, which is half the radius of, half the length of the rod. That's because that's where it was hit. At every subsequent time, it's going to get further and further away from the origin. So the distance separating the point mass from the origin gets bigger and bigger. So if I want the distance of closest approach, or the closest distance, closest point the mass ever gets to the origin, that happens at the very beginning, or at L/2. Its momentum is mu. And it's also positive because it tends to rotate counterclockwise about this point. The final energy. This guy is moving. This guy is moving. And it's rotating. And at this point, the heavy lifting is done. What's left is the math. First, I'll conserve momentum. The initial momentum is 0. The final momentum is mu, negative, plus big MV, which is telling you that big V is little m over big M u. Doesn't solve my problem, but it gets me part way there. Angular momentum is conserved. That means that 1/12, or I omega naught equals this. I omega plus L/2 mu. Energy is conserved, so this one is equal to this one. Now you'll notice that conservation laws give me 3 equations. And coincidentally, actually not coincidentally, by design, there are 3 variables in the problem. I don't know u, I don't know v, and I don't know omega. But since I have the 3 equations by conservation laws, I have enough equations to solve for them. And at this point, it becomes a mess. Basically, I could solve for v in terms of u. I could solve for omega in terms of u, stick them both inside here, and figure out an equation for u. Let me do that. If I solve for omega in terms of u, I'll move this term to the left and divide by I, excuse me. Then I put it all in here. I would have 1/2. Well, the 1/2s all cancel because each term has a 1/2. I have I omega naught squared equals mu squared, which I don't change. But I have a v here, so I'll substitute this v into here. So I'll get my u. I have to square it. And then I have my I term. And I end up getting 1 equation and 1 unknown, because the only term I don't know in this equation is u. Remember, I already figured out what I is. I is 1/12 ml squared. And at this point, it's a whole bunch of algebra. This gives me, since there's a u squared common in both, I'll factor out mu squared from both of these terms, and I'll get well, when I expand this term out, I get yeah, because it's a pain in the rear to write. I mean, it's not a simple variable, right? It's like 1/12 ml squared, right? Yeah, it's, if you put it in, you're just going to carry so many variables. It's going to be tedious. Moreover, it's going to be a source of error. Because when you go from one line to another, you have to copy it down again, and you might drop the 1 here and write a 2 instead of 12. You're welcome. This term will cancel out this term. And basically, you'll find that you don't get a quadratic. Well, it's a very simple quadratic to solve. Namely, either u is 0, Yeah, it was a solution because it was the initial state, right? When u was 0. Or you can factor out a u and you'll get a linear equation that you can solve. Okay. I'll let you do this because I'm pretty sure I'm already putting the few of you who are coming to lecture today to sleep because of all this algebra. Okay. But do go through this algebra. I know it's tedious, but it's good practice as well. Now, I did these 3 examples for angular momentum because each of the 3 examples, well, they had different things conserved. The first one only had angular momentum conserved, the second one had angular momentum and linear momentum, and the third one has all of them conserved. And as there's more conservation laws being applied to the problem, the algebra becomes more tedious and it becomes a harder problem. Now, someone asked me if I can show you an example where angular momentum, where there is an external torque. I can't do that because all the examples here, angular momentum is conserved, but I can show you something different. If you remember the first example we did, where there was a mass, point mass moving in, it was going to collide with a rod, and this rod was pinned here, and we're saying that there was some force that was exerted by the table, keeping the rod here during the collision. Okay. And as I mentioned to you, that angular momentum was conserved if you choose your origin to be at the pin. Because then any force, any torque exerted by this external force, this is a force external to the system, would be 0 because it's exerted through the origin. If you attempted to do this problem by choosing your origin to be at the center of the rod, like we've been doing in these 2 examples, well, you can choose that origin if you wish, but you'll find that angular momentum is not conserved about this point. That's because there's this force here which will exert a torque on the system, and this force is external to the system. So it gives an external torque. Basically, angular momentum in general may or may not be conserved about a specific point that you would choose. About certain points, it can be conserved. Well, it's conserved if you choose this point as your origin, for example. But at other points, it's not. If you chose this point, there would be an external torque on your system, and angular momentum would not be conserved. So the rule of thumb is if there is a pivot point, a point about which everything is rotating, choose that point as your origin. But you already do this, right, for torques. If there isn't a pivot point, choose a center of mass as your origin. Right? Those are probably the 2 safest choices. And you do that for torques as well. Okay. They just apply to angular momentum conservation as well. Questions? Questions about rotating motion in general?
Do you mind putting the other board back down?
Sure. Well, I'm going to start transitioning over to statics, so I'm going to start erasing the boards. If you do think of a question, please do ask.
Just to confirm what you said, if there is no pivot point, it's best to choose the center of mass as the origin, but if there is a pivot point, it's best to choose that as the origin?
Yeah.
Okay.
Yeah. It's safest to do so. I'm not saying that it'll work 100% of the time, but it'll work most of the time.
Professor?
Yes.
One of the lines was by the stick, well, they're kind of ultimately right. So I'm just wondering what the lines the third line from the bottom is.
Is that better?
Yeah, I can see it. Thank you.
I can move it back and forth if you want. I can't move this because I want to use this as a demo in a few minutes.
I see.
You're welcome. Yeah, go ahead.
So for the I term in your second to last line on that problem, what is the NL, W?
When it comes from me expanding this out, right? So when I do this product, it's the cross term.
Okay, got it. Thank you.
You're welcome. This should teach me not to write so hard. All right. I'll keep that as that for now. Statics. We're only covered a piece of statics that's covered in this lecture and on the lecture notes. That's it. There's a lot more. Statics cover a lot more, but we're not getting into it. We have other things we have to focus on. If you go by its name, statics, you would say, hey, in statics, nothing moves. Not quite true. Or you say, hey, if nothing moves, isn't it really boring? Not really. Think of it this way. This building that I'm in, the building that you're in right now, doesn't move. It better not move. And yet to design the building and to make sure that after it's built, it doesn't move, you need to use statics. You need to analyze properties, the forces acting on what's inside the building and what's used to build the building. And so statics turns out to be quite important, especially for those who are majoring in architecture. And there's probably a few of you in this class. Or for those who are doing civil engineering, who don't, and they don't take this class. They take the 7 series. But from our perspective, statics is a lot simpler. Because in our perspective, often when we're dealing with statics, one of the accelerations is zero. Statics, well, here. In statics, there's two criteria. The first criteria is called, I don't want to get the name right, so let me copy it down. Or the first condition for equilibrium is called this. The first condition for equilibrium is that the sum of forces on the system you're dealing with is zero, which automatically means that the center of mass acceleration is zero, which means that you don't have to deal with A's, the accelerations in this case. The second condition for equilibrium is that the sum of torques is zero, which means that if the second condition for equilibrium holds for your system, there's no angular acceleration, which is basically telling you that things aren't rotating, or not in that sense that we have to deal with. Right? But you should be aware that you can have systems for which the first condition of equilibrium holds, but the second does not. You can have systems for which the second condition for equilibrium holds, but the first does not. Or you have systems for both, where both holds. This is one of them. This is basically a rod with mass big M, horizontally connected to this pivot point by a hinge. The other side of it is connected to that point by a chain, and there's an additional mass of 2 kilograms at the end. Okay. Nothing moves here, and we want to make sure that nothing ever moves. We want to make, and that means that we have to know what the force on this hinge is to make sure that the hinge never breaks, given the mass of this rod and the mass hanging here. And we also have to know what the tension through this chain is, so that this chain doesn't break and this whole thing fall down, given this mass and this mass, and the length of that rod. In other words, statics also often comes down to determining exactly what the forces and torques that are acting on the system for a specific configuration. Now, before we analyze this system using the conditions for equilibrium, doing one more example, we should talk about stable and unstable equilibria. Okay. Now, when I say the first condition for equilibrium and the second condition for equilibrium, that's about a specific point or a specific configuration of your system. Yeah, let's do it this way. Let me move my computer over so I can get this into view. Okay, this is a chair. Okay. This chair is in equilibrium The sum of forces on it is certainly 0. The sum of torques on it is 0. Okay? So when it's in this position, it's in equilibrium. The question is whether or not the equilibrium position is stable or unstable. By a stable equilibrium position, what we mean is you can take your system, move it a little bit away from its equilibrium position, and then see if it returns to the equilibrium position. That's a lot of words, and let me show you. This is the equilibrium position of this chair. There's many ways I can move it, but one way I can move it is simply to do this, to tilt it, right? Which means that I am changing the second condition for equilibrium. And if I let go, the chair returns to the equilibrium position. In fact, I could push it the other way. If I let go, the same thing happens. That means that this configuration, at least for rotating about this point, is a stable equilibrium. I move the system a little bit off the point, I let go, the system automatically returns to the equilibrium position. To show you an unstable equilibrium, well, that's harder. Okay. If I'm really, really careful, there will be one specific position of this chair, such that when I let my hand go, the chair won't move. That also is an equilibrium position because it will satisfy both the first and the second condition for equilibrium. It's just really hard to find because that's one specific angle. It's roughly here. It's an unstable equilibrium because if I move my chair a little bit away from the equilibrium position to the left, let's say, it'll move away from the original position. It won't move towards it. And if I move it a little bit to the right and I let go, it'll once again move away from the equilibrium position. So that's an unstable equilibrium position. So the chair can have both a stable and an unstable position. Okay. There's also what's called a metastable position, and I won't worry about that. Now, let's go back to here. As I said, I'm interested in the force that's exerted on the hinge, so I don't want that force to be too big, and the tension in this chain. So I want to calculate both. Here's the wall, here's the hinge, here's the rod. The rod has mass big M. And at the very end of the rod, I hang a mass little m. This mass here, which isn't hanging, it's just placed at the end of the rod. And there's a chain that goes from the rod to the end of, from the rod to the wall. I'll give you this angle, because that's how this whole thing's made. This system doesn't move, period. So there is no accelerations. That means A is 0, that means alpha is 0. That means the first and second condition for equilibria are met. And here's an important point. Remember that when we calculate torques, and we'll have to calculate torques because there's a second condition for equilibrium. When we calculate torques, we have to choose an origin. And remember that I told you either you choose the pivot point or the center of mass of the body if the body's moving. In this case, because there is no angular acceleration, this body isn't moving, you can choose whatever point you wish to calculate torques about. So as a rule of thumb, choose your origin, choose the point about which you will calculate your torques at the point through which the most number of unknown forces act. That's just a rule of thumb, and I'll show you what I mean in a minute. Let me draw the free body diagram for this system. In other words, let's do step 1. And yes, steps 1, 2, 3, 4 still hold. I know that there's a force on this rod with mass big M exerted at this hinge. I don't know what the direction of it is, but I need to draw it in. There. Just choose a direction. I know there's gravity acting through the center of mass of the rod, which is at the middle of the rod. I also know that there's gravity acting through this guy, through the hanging mass. And I know that there's tension, is parallel to the chain, so it goes up like this. In other words, that's step 1 of everything we've done. Now, I could have drawn a separate free body diagram for this little mass, putting in a tension and everything, another tension. That's perfectly fine. I wanted to short circuit this a little bit because I wanted to have time to do another example where only the second condition for equilibria holds. Step 2 would be I have to sum the forces and sum the torques. Well, since I have to sum torques, I have to choose an origin about which I will sum my torques. And since there is no angular acceleration, I could choose any point I want. I'll choose this one. Why? Because I don't know FH. That's all. And because now FH acts through the origin, FH provides no torque.
Professor, why is FH in that direction?
I'm just guessing.
Okay.
I have to choose one, right? So what the heck, I'll just draw it in. If it turns out to be wrong, I'll just get a negative sign, and that's fine. Step 2, I'll sum my forces. If I sum the forces along the x direction, I get the x component of FH, which is to the left. And I have the x component of t. And I want the piece of t that's parallel to the rod, which is adjacent to my angle, so that's t cosine theta. And it's also negative because it's pointing to my left. Then I sum the forces along the y direction. I get the vertical component of t. That will be t sine theta. I'll get mg pointing down, little mg pointing down, and the y component of FH pointing down. And then the third thing I have to sum is the torques. FH acts through the origin, so it provides no torque. R is 0 in that case. mg, however, acts at a distance L over 2. Now, I didn't give you the length of the rod, but I need it to calculate the torque, so I'll introduce it. Just have to make sure that my final answer, in other words, my expression for FH and T, doesn't contain it. The distance from the pivot point to the point at which the force is exerted is L over 2. Times mg. The angle about the radial line in mg is 90 degrees. Sine of 90 is 1. And this guy tends to rotate everything in a clockwise direction about the pivot point, so this torque is negative. Similarly, this guy provides a torque. It's at a distance L from my origin. It also wants to rotate everything clockwise about this point, so it's negative. And then I have the tension. The component of tension that points inward doesn't provide any torque. The angle between the force and the radial line is 180 degrees, and sine of 180 is 0. No, the only piece that provides torque is the one that goes upwards. That was T sine theta. So the torque provided by the tension is L, since it's a distance L from my origin, T sine theta. And it's positive because it wants to rotate everything in a counterclockwise direction about this origin. Then I do step 3. Well, step 3 is easy. All the accelerations are 0. Nothing's moving. Step 4, set F equal to ma and torque equals I alpha, and solve. This one gives me and this one gives me well, the first equation just tells me that FH in the x direction is negative T cosine theta, which already tells me that the x component of FH was wrong. It actually points to the right and not to the left. That's okay. This one tells me that the y component of FH is T sine theta minus little m plus big M G. While the last equation tells me what T is. I'll cancel out all the L's. I'll move these two equations, these two terms on the right-hand side, and divide by sine theta. I now know what the tension is. Sticking my tension into here, I get that FH in the x direction is negative little m plus 1/2 big M G over times cosine theta divided by sine theta is 1 over tangent theta. FH in the y direction becomes or negative 1/2 big mg. So I got my hinge force, I got my tension, and I've solved the problem. But if you look at how I solved the problem, I just did it exactly the same way we've been doing for the whole semester. There's nothing new here. The only thing that's new is alpha and A is 0. And you could choose your origin to be wherever you want when alpha is 0. Questions?
Foresee the hinge was in the wrong direction.
Excuse me? Oh, because there's negative signs here. Right? They're actually pointing the opposite direction than I drew. I mean, it's not wrong. When we wouldn't take off for it on an exam. It's just different than what I drew.
It's going in like the negative X direction.
It would actually be here. The actual direction for FH would not be this. It'd be somewhere here. It'll be that way. Okay, the second example of statics I want to do for you is more of a dynamical system, dynamical stability system. It's basically how fast a car can turn in a circle without it flipping over. What I mean by that is the following. I have a car, and it has center of mass velocity v, and it's turning around in a radius r. Okay. So if I look at the system from here, this direction, I see my car. I see the ground, and this is the center of the circle. Now, you're told the width of the car, how wide the car is, the distance between the wheels that's on contact with the ground. You are told the center of mass height. The center of mass is here, and the height above the ground is this much. Okay. I want to know what is the fastest, what is the biggest V can be if this car doesn't flip over onto its top. Now, I'm going to assume that static friction is going to be big enough so it never slides, right? So now I'm going to worry about static friction and whether or not the limit of static friction. Right? I'm going to assume that it is always big enough. I just want to know what is the biggest V can be so it doesn't flip over. Now, the fact that it's moving in a circle or part of a circle means that that car, right? That car is accelerating because it has centripetal acceleration. Since it is accelerating, it does not satisfy the first condition for equilibrium. The sum of forces isn't 0. But I don't want it to flip. If I don't want it to flip, what I mean by flip is the car is like this. I don't want it to go like this, like you see in the movies all the time. And since it can't go like this, that means that the sum of torques must be 0, because I don't want it to have an angular acceleration. If there is an angular acceleration, it'll start flipping. I don't want that to happen. Which means that it satisfies the second condition for equilibrium. The sum of torques has to be 0. Moreover, I don't want everything to go this way, and I want the biggest V so that that happens. Well, in general, there'll be a normal force on this wheel and a normal force in this wheel. But if I want the biggest V so that it just starts to flip, the normal force here on this wheel will be 0, because this wheel will just start losing contact with the ground. The only normal force present will be on this wheel. That's the important point. That's the essential physics you have to realize about this problem. Okay. So let me draw the free body diagram. There is mg pointing downwards. There is a normal force pushing up. And there is friction going inwards. Fs. Right. Now, this body is accelerating. And remember, I told you that as a rule of thumb, because the sum of torques isn't 0, you can choose wherever you want to choose to as your origin about which you calculate torques. That's a rule of thumb that's violated at times. It's violated here. You really do need to choose your origin, in this case, to be at the center of mass, because this body is accelerating. And remember, when a body is accelerating, you're safest to put it at the center of mass. So step 1, sum the forces. Along the x direction, there's only static friction. It's pointed in the minus x direction, so it's negative Fs. The sum of forces along y gives me the normal force minus big mg. Then the sum of torques. Well, the normal force provides a torque. Okay. It's a positive torque because it wants to rotate everything clockwise about this point. It's equal to the magnitude of the normal force times the sine of the angle between the radial line and the force times the distance between this point and here. Or, instead of thinking about those terms, it's equal to this. It's equal to that length that's perpendicular to n, and it goes from the origin to the force vector. This is called the lever arm. The book uses it quite a lot. I haven't until now. Because we've been writing the torque as F times R times F perp, where F perp is the component of the force that's perpendicular to R, the radial line. Another way of writing this as R perp times F, the perpendicular distance to F, and that's the lever arm. turns out that for statics problems, lever arms are more useful than this form of it. Either will work. It's just faster to use lever arms because the perpendicular distance is this much, which is precisely W over 2. Friction also provides a torque. Pulls this way. It wants to rotate the car clockwise about the pivot point, so it provides a negative torque. The perpendicular distance, or the lever arm, is this much, which is precisely the height of the center of mass. Okay. Step 3. The acceleration in the x direction is negative v squared over r. This is because, well, circular motion. And the acceleration in the y direction is 0. Step 4. Sum of f equal to ma. This one becomes this one becomes, well, this one becomes this one tells me what the static friction is mv squared over r. This one tells me what the normal force is big mg. If I plug it in here, I'll get W over 2, big mg, minus h times mv squared over r equals 0. The m's cancel out. And when I solve for v squared, I move this to the right-hand side, multiply by r, and divide by h. After taking a square root, I get that. In other words, it depends on the ratio of the width of the car to the height of the center of mass. If I want to be able to make that term at very high speeds where v is really big, I want this ratio to be as big as possible. I want my w to be large and my h to be small. In other words, I want my car to be wide and low, which is precisely what a sports car looks like. Sports cars are designed so they don't flip over when they make a turn at very high speeds. You want that ratio to be as big as you can. Well, I'm exactly on time. I will see you tonight. At least I will be in one LeConte this evening. Well, see you tonight and hopefully on Thursday.
Thank you.
You're welcome.
Professor. Thank you.
You're welcome.
Can I ask you one last question?
Sure.
So for your free body diagram for this car, the normal force, or when you're calculating the torques, the normal force is acting from the bottom of the wheel, right?
Yes.
And so how is it that the distance is only W/2? Wouldn't it be like kind of like a hypotenuse of a triangle?
Yeah, I'm using the lever arm, so I'm trying to find a perpendicular distance to the force. Right?
Okay.
Right. And that's this distance. You're right. Before we were using this distance, but we're also using this angle. Okay. And the combination of that distance.
Okay.
Right. Okay?
Yeah, thank you.
You're welcome. Okay. All of 10 people came today. No, this week.